Hello everybody, welcome to the course VLSI Design Flow RTL to GDS. This is the 42nd lecture. In this lecture, we will be discussing post layout verification and sign off. In earlier lectures, we had looked into various physical design tasks such as chip planning, placement, clock tree synthesis and routing. So, at the end of detailed routing, we have basically created the layout which is complete, and this layout can be used by the foundry for creating the chips or manufacturing the chips. However, before sending the final layout or this layout that was created after detailed routing to the foundry, we do some post layout verification to ensure that our layout is indeed carrying out or delivering the functionality that we wanted, and also the figures of merit are acceptable. So, in this lecture, we will be looking into what are these post layout verification tasks that we will need to carry out after detailed routing and before sending the final layout to the foundry for fabrication. Specifically, in this lecture, we will be looking into layout extraction, physical verification, ECO or engineering change order, and sign off. So, first let us look into layout extraction. Now, what is the motivation of layout extraction? So, when we have created a layout, basically the layout is nothing but various shapes or polygons that we need to or the shapes or polygons that needs to be fabricated on various layers during fabrication or during photolithography, right. So, layout is composed of various shapes or polygons, right. Now, the various verification tools such as static timing analysis tool, signal integrity tool and other physical verification tools, if they work directly on the layout or directly on the polygons that are on the layout, it will be very difficult or challenging task for them to do the computation and carry out the verification. Therefore, what we do is that once our layout has been created, we have the final layout has been created after detailed routing, then we extract various information from the layout. Using the layout that was created, we extract out some information, the useful information that are relevant for post layout verification, and then give it to the tools, various tools, for example, tools that do the timing analysis, power analysis and other types of analysis that are needed in the post layout verification task. Those take the information or take the extracted information and do the analysis, and with the help of when they get the extracted information rather than the complete layout, then the computation becomes easy for this post layout verification tools, and this is the primary motivation of doing carrying out layout extraction. Now, layout extraction consists of two major tasks, and what are these tasks? The first is circuit extraction or devices and interconnections, those are extracted from the layout, right. Now, we have created the layout and layout consists of polygons. Now, the layout extraction tool will first extract out various kinds of devices meaning transistors and other things that we have actually created on our layout or we intended to create on the layout, and the interconnections meaning the nets that we created during detailed routing or say during the power grid that we created or the clock mesh that we created and so on. So, those interconnections and the devices are first extracted during the circuit extraction step. Then in the next step, what is done is that the parasitics are extracted, right. So, the parasitics are various resistances, capacitances and inductances that are associated with the layout but which we did not intend to create, that they get created on its own, right. For example, coupling capacitance between two wires, right. We don't intend to create those capacitors, but those capacitors are created automatically, or those parasitic capacitors exist in the layout, and that information also needs to be extracted by the tool, so that say signal integrity tool can can comprehend that how much the capacitance is between two lines, and based on that it can check whether signal integrity issues is there in our layout and do we need to fix them and so on, right. So, now let us look into these two tasks, that is circuit extraction and parasitic extraction, in some more detail. Now, in this figure we are showing the framework on which the circuit extraction tool works, right. So, this is the circuit extraction tool, right, the circuit extraction tool, and it takes these two inputs, right. The inputs are coming here, right. So, what are the inputs? So, the first input is the merged GDS, right. Now, what do we mean by merged GDS? So, once we created our layout, right, when we did the created our design and done and carried out say the routing of the detailed routing also, then our layout was created. In the layout, at this stage what happens is that we have abstract view of the cells, right. For example, the cells, for example, an inverter or say AND gate, these are the standard cells. Now, the view of these standard cells are an abstract view, and these views are based on say what is the view in the left file, right. So, remember that when we carry out physical design, we give library which is one of the format is in the left format, and the left format consists of abstract view of the cells. So, it knows that where the pins are, what is the bounding box and so on, but it does not know the exact layout of the inverter. For example, if this is an inverter, then the exact layout of that, how many PMOS are there, how the NMOS are there, and how the connections is made on the layout internally in this inverter, that is not there. That information is actually present in the GDS file or the layout file of the standard shells and macros, and those these files will also come from the PDK, but then we have to merge these two information, right. So, the design or the post layout design, this contains an abstract view of the inverters and how the various kind of standard shells are connected and so on, but the internal detail of the inverter layout, that is there in the library or in the GDS of the standard cells which is contained in the PDK, we need to merge these two information, and then the merged GDS is basically the final layout that can be used for fabrication, right. Now, physical design tools have capabilities to simply merge these two information, and they will create that they can give us a merged GDS, which we can give it to the circuit extraction tool, right. Now, circuit extraction tool, what it will do is that it will take the information of the extraction rules using say LVS or ERC rule deck, right. So, then what is a rule deck? So, rule deck basically are set of instructions that are coded in some format in a format, so that this circuit extraction tool can comprehend that how to extract various kind of devices from the layout. For example, the rule can be that if there is a poly and it is intersecting with say diffusion layer, then that is an indication that there is a transistor at the intersection, right. So, similar kind of rules will be coded or instructions will be coded in the rule deck, and using those instructions or the extraction rules, the tool will be able to extract various kind of devices from the layout, right. Now, these extraction rules will come from the foundry and it will differ for different technologies. For example, say for 22 nanometer, it will be a different set of LVS or ERC rule deck, or for say 7 nanometer, it will be quite different, right. So, the information that how to extract the devices from the layout, that comes from the rule from the foundry, and it is encoded in in some format that the tool can understand, and the file that we use in our design flow, those are known as rule deck. So, in this case the LVS rule deck or ERC rule decks are typically used for circuit extraction, right. Now, what will be the output of the circuit extraction? So, the first output will be the layout netlist, right. So, what layout netlist means, that from the layout the extraction tool will create a netlist. For example, if this is say an inverter and this inverter is connected to another inverter like this, right, on the layout, then the tool will extract that information and generate a netlist which is typically in the SPICE form, right. So, in the SPICE form we can describe that how many transistors are there, how they are connected and so on, right. For example, if this is an inverter, right, this is one inverter I1, this is another inverter I2, right. Now, we know that CMOS inverter consists of a PMOS and an NMOS, right. So, we will have something like this, some structure like this, we will have PMOS, NMOS, right, and this will be the ground line, and then this is the power line, and this is the output of this inverter, right, this is the output being fed to the next inverter, right. So, this is the next inverter, it will be fed to this, right. So, the circuit extraction tool will basically generate a netlist of this form and will be typically generated in a format of SPICE, right. So, this is what the layout netlist is, meaning that this netlist has been created or extracted out of the layout that was given to the tool. Additionally, the circuit extraction tool can also give ERC report, right, because during circuit extraction if the rule deck contains the ERC rules, that what are the connectivity rules or the rules for having valid connectivity, then the tool can also find out what are invalid connections, right, and those can be reported during the circuit extraction. Now, what is parasitic extraction? Now, parasitic extractions are basically the unwanted resistance, capacitance and inductance which are created on our layout, right. We did not want intentionally to we did not create intentionally these resistors, capacitors and inductors in our layout, but they are automatically created because of the way we make the interconnections and so on, right. So, in the parasitic extraction, what the parasitic extraction tool will do, it will extract all these resistance, capacitance and inductance value from the layout and report it in some format, right. So, the resistance is extracted for each net on the layout, and while extracting it, what the tool can do is that probably consider a net and then segment it into various sections, right. And for each segment, the tool can estimate or compute the resistance based on its sheet resistance, length, width and so on, and then report and combine the result of various segments to get the resistance of the complete net, and then this process will be repeated for all the nets in our design. Now, capacitance extraction needs to be done such that all the various components, right, the components that we discussed in our earlier lectures. So, if there are wires, right, and there are other wires in its vicinity, then there are various kinds of coupling capacitances, and there are and the coupling capacitance can also be of various types, right. We have seen that the coupling capacitance can be because of fringe, because of lateral proximity between two wires, or because of the overlap between two wires and so on. So, all these components needs to be considered while capacitance extraction. So, in general, capacitance extraction is a more difficult problem than resistance extraction. And what tools typically do, that if at the chip level, when we have lots of nets in our design or in the layout, and we need to compute the parasitic capacitance for all of them, the chip level parasitic extraction is decomposed into two tasks, right. So, what are these two tasks? The first is technology pre-characterization, and the second task is pattern matching, right. Now, let us look into these two tasks more carefully, right. So, what is technology pre-characterization? So, technology pre-characterization is performed only once for a given technology. Maybe when say 7 nanometer technology is being developed, then we have to do pre-characterization of technology pre-characterization for that given technology, and subsequently the information that comes out from pre-characterization for a given technology, it will be used for many designs, right. Now, what is done in pre-characterization step? So, in pre-characterization, what the tool will do is that it will enumerate millions of sample geometries and structures, right. Now, however, these millions of sample geometries and structures created or for a given technology, so it comes from the stack of the interconnects and the devices that can be there for a given technology, right. So, based on which the different stack of interconnects layers and the dielectric, the tool will come up with various combinations that can be there between different metal layers, right, and also various kind of in addition to various combination, the tool will try out various geometries, right, or different kind of spacing, and which in which conductor or which metal layer is in proximity with other metal layers, and so on, right. So, based on the gate stack or sorry, the technology stack and the interconnect stack, the tool may come up with say one combination, like the metal 1 is there, M1, and say M2 is just above it, M2 is just above it, and say another M2 layer is somewhere here, right. So, this is one configuration that the tool may come up with, right. Now, similarly, there can be many such combinations and different kinds of geometries and configurations of the metal layers, and the tool will enumerate them, and can be millions of such combinations can be there, and for each of them the tool will uh, compute the capacitance using more accurate field solvers, right. Now, what are field solvers? So, field solvers do numerical computation, right. So, it divides the structure into meshes and do a numerical computation and computes the capacitance very accurately using sophisticated techniques. So, using these field solvers, what the tool will compute the capacitance for various configurations or different geometries and structures, and then it will put the capacitance value either in a lookup table, or using the capacitance value computed for various structures, it can come up with some empirical formula created using curve fitting, right, and that empirical formula will be stored during the pre-characterization step. Now, this pre-characterization task is very time consuming, but fortunately we need to do it only for once for a given technology, and this information will be utilized by all the designs that will be fabricated using this technology, and therefore, the cost invest or effort gone into technology pre-characterization, that gets distributed or get amortized over multiple designs, and the effective cost of technology pre-characterization comes down, right. Now, the second task in parasitic extraction is pattern matching, right. Now, this pattern matching is layout specific, right. Now, what is done in pattern matching is that we partition a layout into smaller windows, right. So, if there are big partition, there is a big layout, it will be partitioned into small windows, right, and then match windows with pre-characterized partition, right. So, suppose this is the window in our layout, this is our layout, then this window will be matched with some pre-characterized configuration, and if it matches, right, then it will compute the capacitance with the help of lookup table or empirical formula that was stored for that configuration during the pre-characterization step, right. Now, during this computation, the tool will use the actual geometries of the layout. Then let us now look into what physical verification task we need to carry out after creating the layout. So, there are three major physical verification tasks that we need to carry out. The first is design rule check or DRC, the second one is electrical rule check or ERC, and the third is layout versus schematic check or LVS. Now, we will be looking into all these three tasks in some detail. Now, what is design rule check? So, design rule check basically ensures that the layout meets the constraint required for manufacturing, and these rules are basically defined by the respective foundries. So, we have, say for example, created a layout for say 14 nanometer, then we will use the design rules that will be coming from the foundry where we want our circuit to be fabricated. So, it will be coming from the foundry that has actually given us the libraries PDKs for 14 nanometer based on which we have designed, right. So, the PDK will also contain the design rules that needs to be checked, right. So, why do we need to or why do foundry try to enforce these design rules? So, the basic motivation is that if these design rules are followed, or those are ensured that this design, or we ensure that these design rules are honored in our layout, then we will be able to achieve good yield and also improve the reliability of our circuit, right. So, this design rules can vary with the technology, and typically what happens is that as the technology progresses, the feature size decreases, and at smaller feature size these rules become more and more complicated. So, this figure shows basically the framework of design rule check. So, for design rule check, so this is the basic tool that carries out performs design rule checking, right. Now, what are the inputs? The input is the first input is the layout database, right, that is the merge GDS that we discussed in previously, and then these DRC rule deck. So, this will contain basically the rules that needs to be followed in the layout, right, and using these two information, the design rule check will design rule checker will generate a report or DRC report, and if we find violation, then we need to fix those violations, right, and this has to be done iteratively until we have fixed all the violations, design rule violations. Let us look into a few example of design rules. For example, there can be a design rule which says that the minimum width of poly should be a given value, say W, right. Now, if in the layout this the width of this poly is smaller than this W, right, then it will get violated, it will be flagged and it will come in the DRC report, right. If, and now to fix this, what we have to do? We have to increase the width of this poly, right, so that it becomes more than W, right. Similarly, there can be a rule that the spacing between two polys should be at least S, capital S. Now, in our layout, if this spacing is less, right, then the tool will flag that there is a violation of minimum spacing, right, and this will be there in the DRC report, and then looking at that we will need to fix it. For example, in this case we have to make the spacing larger, more than the defined capital S, right. Then once we have created the layout, we also need to check for ERC or electrical rule check. Now, what does electrical rule check do? It basically check design for electrical connections that can be problematic, right. So, the connections which can be problematic, those are flagged, and then we have to fix those things, right. For example, the problems can be of the shorts, open, floating gate, floating nets, etc. Right. So, when we do say circuit extraction, probably at that time if the rule deck contains ERC rules also, then ERC report will be created at that time, and then we can fix without going into further down the flow. We can just look into the where this the rule violation was there, and we can fix it. Now, what is LVS? LVS is basically layout versus schematic check, right. It verifies whether the layout corresponds to the original schematic netlist of the design, right. So, we started physical design with the netlist, right. So, after logic synthesis we got netlist, and then from using that netlist we have created, we have gone through physical design task, and at the end of that we have our layout, right. Now, we want that the layout basically delivers the same functionality that our original netlist was delivering, right, and that is what the basic purpose of layout versus schematic check is, right. Now, let us look into the framework of layout versus schematic check. So, this framework looks very complicated, right, but it is not that complicated. What is layout versus schematic check is doing is that basically it is doing comparison of two entities, right. So, this is the basic task that is being performed by LVS, right, LVS. So, it is doing comparison of two netlists, and what are these two netlists? The first netlist is the extracted netlist, right. So, the layout netlist that we extracted. Remember that when we discussed circuit extraction, we said that given our design and the libraries and the PDK which contains the GDS of each individual standard shells and macros, we created a merged GDS, and using merged GDS we did a circuit extraction, right. And the circuit extraction, when we did, we get the layout netlist, right. So, this portion is the same that we discussed in layout extraction, right. So, the layout netlist that we got from layout extraction, that is compared with the source netlist. Now, what is the source netlist? So, source netlist is the logical netlist combined with the device information, right. The source netlist contains the information of the netlist, or it is the same netlist that we started the physical design with, right. So, the after logic synthesis we got a netlist, right. Now, that netlist was consisting of that, say, how the AND gate was there, NAND gate was there, and inverter was there, how they were connected, and so on. So, that information is in the logical netlist, right. Now, with the logical netlist we combine the device information, right. For example, if we have, say, an inverter, right, this inverter internally contains a PMOS and an NMOS, right. So, this information is also contained in the PDK, that each standard cell consists of which all transistors and devices and so on. So, that information is again taken and merged with this logical netlist to get the source netlist, and these two, source netlist and the layout netlist, these two are compared. If the comparison is successful, right, then we are done with that. If the LVS report is there and it shows some violation, right, that if there are some discrepancies, then we need to go back to our layout or our design and see that whether what is the problem, and then probably fix it until the layout versus schematic check passes, right. Then now let us go into the sign off, right. Now, we now the after we have created the layout, right, now we want to basically do post layout verification in a thorough manner and sign off only after all the checks are passing, right. Now, what is sign off? Sign off is a series of verification steps that must be carried out before sending the layout or GDS to the foundry, right. Now, why do we do sign off checks? We do the sign off checks because these checks ensure that the layout delivers the intended functionality and also meets the various figures of merit that we intended, right. So, let us look into the framework of sign-off check, right. So, in the sign-off check, what will be done is that we have the design layout. This layout was created say after a detailed routing, and then from this layout we extracted design information. We saw what the layout extraction is, and using layout extraction we got various information like what are the parasitics, what is the net list, and so on, right. Now, using that information, a series of checks will be done, right. So, here I am showing some of the checks like static timing analysis will be done, then physical verification task will be done, LVS, ERC, DRC that we just discussed, right. And then there can be signal integrity checks, right. Now, note that once we have created the layout of the interconnects, then only we can extract the coupling capacitance, and then only we can do the signal integrity checks, right, more precisely or accurately. So, after we have created the layout, we do the signal integrity checks. We also do power integrity checks. For example, say it can be related to IR drop in the power lines, or it can be related to electromigration checks and so on. So, after creating the layout of the interconnects, carrying out these checks becomes more accurate or more reliable, and therefore, after we have created the layout, we need to carry out these checks again, even though we might have carried out these checks earlier in our design flow, right, because the accuracy at this stage is much higher than the accuracy we had earlier, right. And there can be other checks which can be defined by a design house or the company which is designing, or a designer can also say that these are some of the more extra checks that we need to do before sending it to for the tape out, or before sending it out to foundry for fabrication. Now, typically what is done is that these sign-off checks are done using a separate set of tools that we use during the implementation phase, right. So, implementation phase we use some tools which whose major purpose is to implement our design, right. They also do some checking, for example, related to timing, related to say DRC and other things. But the accuracy of those checks are not they do these checks at a higher level of abstraction, and therefore, the accuracy of those checks can be lower, right. Therefore, once we are going to sign off, we take another set of tools which are separate from the implementation tools. So, those we take help of sign-off checking tools which have got much higher accuracy for carrying out carrying out these kind of verification, right. Now, if we find violation at this stage, right, now we have done everything, but we are getting a few violations, right. Now, how to fix those violations, right. Now, if we want to fix those violations, we might need to change our design, right. So, therefore, we again go into the implementation phase, right. So, if we are lucky, then we can basically make changes in using ECO. What is ECO? We will just see. Or if we are not that much lucky, then we might need to go back and fix issues, say in chip planning if we are highly unlucky, or in placement, or in clock tree synthesis, or in global routing, or in detailed routing, right. So, if the fixes are localized or as close to the end of the design flow, then the cost and the effort for fixing will be less, right. If we find a problem which is deep rooted at say very early in the design flow, then the cost of fixing is much higher, right. And therefore, at the sign off stage, can create loops in our design flow, right. So, these can create loops in our design flow, and we might to carry out these design task, the design task that I have listed in this figure multiple times before the design closure is achieved, right. Now, if there are localized changes, right, localized changes, then we can take help of ECO and to fix those changes or do those changes to our design. Now, what is ECO? ECO stands for engineering change order, right. So, this is a mechanism which is through which we introduce controlled changes in our design, right. So, why do we want to or when do we when will be needing to carry out these controlled changes or ECO changes? So, sometimes at last moment incremental changes is needed in our design, right, and these incremental changes can be because of a bug that was discovered very late in the design flow, or some functionality change request came much later and in the when we have in the design flow, and we are forced to make those changes. We cannot avoid those changes, right. So, if such kind of changes are there in our design which are coming at the last moment of the design flow, then we have to be very careful, right. Why? Because these changes, last moment changes, can be very risky. It can introduce new errors, and therefore, we incorporate these changes using engineering change order, right. So, we do it very carefully through the engineering change order mechanism, and it is at the end of this design flow, right. We do these changes, and we take help of what are known as ECO tools. Now, what do these tools do? So, these tools enable making targeted incremental changes rather than re-implementing the design, right. So, if we want localized changes, then these ECO tools help us to make localized changes in our design in a more efficient way and in a better way. Why how does it allow us to do these changes in a more efficient way? These tools not only make changes in our design, but they also help us verify the correctness of the ECO changes. For example, internally it can run a formal tool or timing analysis tool or those kind of tool which will ensure that the behavior of the functionality is not disturbed for our design while making the changes, and therefore, it saves these ECO tools save designer time, effort, cost, and also it minimizes the risk. Now, there are two types of of ECO changes, primarily two types of ECO changes. The first is functional ECO. In functional ECO, we are changing the logic, right. We are changing the functionality of our circuit. Maybe we want to replace an AND gate with a with an AND gate or so on, right. So, though that means there is a functionality change, right. So, it can require logic resynthesis, or we can use the spare cells, right. Remember that in placement stage we put some spare cells and also in our design, right. So, if we do not want to go all the way up to the logic synthesis, we want to make changes only in our physical design or in the interconnections, we can take help of spare cells to carry out these functional ECOs. And there can be some direct changes in the layout to fix setup hold violations, SI related violations and design rule violations. So, these violations will be discovered at the sign off stage, right. So, we saw that in the sign off stage we carried out multiple verification tasks. Now, those tasks can expose new bugs. Now, for fixing those bugs, if those bugs are localized in a small area, we can take help of these ECO tools, and that will help us reduce our designers effort, and also we can also ensure the correctness of the changes with the help of the ECO tools, right. So, we will carry out this sign off verification task. So, here a list of tasks is shown, right, and but do not take it that these tasks needs to be done in a sequential manner. typically when we go to the sign off stage, we are very close to the deadline of completing our project or doing a tape out, right. So typically during that time, it is a kind of a firefighting scenario in the design house, right. And in that case, typically these various sign off checks can be parallelized, given to various groups which carry out them in parallel, so that the design can be closed in a shorter time, right. So once we are free with all these all these verification tasks, shows that there are no issues in our design, or the issues, if they exist, those are tolerable, then we go to the next step, and next step is the design tape out, right. So what is design tape out? Design tape out means that we send the GDS or the layout to the foundry for fabrication, right. So now this design tape out is a kind of a time for celebration for the designers, right, because the arduous design activity that started with, say, system level specifications and then finally culminated in the GDS being sent to the foundry, that concludes the project, right. And therefore, this is an occasion to celebrate for the designers, and it is also an occasion to celebrate for us, because we have come to the end of this course, and we have completed our journey from RTL to GDS. Finally, since this is the last lecture, let me summarize what we have done in this course. So in this course, we started with taking an overview of VLSI design flow, and then we looked into logic design, both implementation and verification. Then we moved to design for test, or DFT, and finally we moved to physical design task, and then physical verification and sign off, right. So in this course, we have covered the entire design flow from, say, from the RTL to GDS, right. So the basic objective of this course was to cover the breadth of the VLSI design flow, which we have done fairly well, right. Now, since this course was of only 12 weeks, right. So at some points we have sacrificed the depth, but for the foundational course, this is acceptable, because we have laid a very strong foundation for this course during this 12 weeks, and over this you can build your expertise on your own. Now, one more thing I would like to highlight is that the VLSI design flow is a course where practical skills are very important, right. So to gain those practical skills, you have to run the CAD tools, analyze those results, and then understand that what goes inside, what is the correct input, what's the wrong input, and so on, right. So in this course, we have given a few tutorials on these open source tools, but I think that you will be able to learn better if you run these tools on your own, analyze on your own, and then that will give you a lot of confidence, and then you can become an excellent VLSI designer, and you will become an asset to the semiconductor industry. Now, if there are any feedback, any questions, I am always reachable. I'll be happy to get your response. You can tell me what went good in this course, what can be improved, and if you have any questions, you are free to reach out to me, right. So I think various kinds of students and participants are there in this course. I wish all of them very good luck and in their future endeavors, and a successful career ahead. Thank you very much.